Okay, so the rate at which fluid filters from the glomerulus into Bowman's capsule is called glomerular filtration rate, or GFR. Okay, typical GFR is about 125 milliliters per minute, or 180 liters per day. So thinking about how that compares to blood volume, I guess I'll just answer this question for you. You might remember blood volume is about 5 liters total in the body, which means that about 30 to 40 times a day, the entire blood volume is making it through your kidneys. Okay. GFR is going to be affected by a couple things. First is the filtration coefficient. So basically, that is a reflection of the characteristics of this interface, right? So that filtration barrier that we just talked about, it's going to reflect the surface area of that filtration barrier and the permeability of that filtration barrier. The second thing that is going to have an effect on GFR is filtration pressure. Okay, so we have a pressure that's driving the movement of fluid from the glomerulus into Bowman's capsule. And I'm going to go into greater detail about that right now. Okay, so you might remember from earlier in the semester when we were talking about filtration and absorption in the capillaries, we had these two opposing pressures, hydrostatic pressure and colloid osmotic pressure, that were going to basically work against each other. And depending on how strong each of those pressures were, we were going to get either filtration or absorption. The same situation is true in at the renal corpuscle. Okay, so basically we have those same two pressures plus another pressure. So let's take a look at that. Okay. Okay, so first pressure we have is P sub H, hydrostatic pressure. As you might remember, hydrostatic pressure is the pressure of the blood pushing against the walls of the capillaries, right? So right here, we're looking at the blood in the glomerulus pushing against the walls of the glomerulus, and that is going to have a tendency to push fluid out of the glomerulus into Bowman's capsule, as illustrated by this red arrow here. Okay. Second pressure is, which you were also still familiar with, hopefully, is pi, or the colloid osmotic pressure. So I want to remind you that colloid osmotic pressure is osmotic pressure due to proteins. Okay. You might also remember that we have a lot of proteins in the blood, in the plasma, but we don't have very many proteins out here. Well, hopefully none, but we don't have very many proteins out here in Bowman's capsule. So that means that osmotic pressure is going to want to draw water in to the glomerulus. Okay, so that's what is indicated by this purple arrow right here. Finally, this is the one pressure that we didn't see in the other capillaries in our bodies. We have this quantity, P fluid, okay, which is the hydrostatic pressure of the fluid that is in Bowman's capsule. Okay, so that hydrostatic pressure is the pressure of the filtrate pushing against the walls of Bowman's capsule, and that is going to have a tendency to push fluid back in towards the glomerulus. Okay. Okay, so we can calculate a net filtration pressure by combining these pressures here. So net filtration pressure is going to be our hydrostatic pressure in the glomerulus minus our colloid osmotic pressure in the glomerulus minus the hydrostatic pressure in Bowman's capsule. Okay, and that's going to give us our net filtration pressure. So guess what you're going to do next? Okay, so let's have you do a practice question. These are our typical pressure values for pH, pi, and P fluid. See if you can calculate the net filtration pressure here. So go ahead and hit pause and do that calculation. Okay, so net filtration pressure, like I said already, is going to be pH minus pi minus P fluid, which is 55 millimeters of mercury minus 30 millimeters of mercury minus 15 millimeters of mercury. That gives you 10 millimeters of mercury. Okay. Okay, so we just went over these factors that are going to affect GFR. We talked about the filtration, like the filtration barrier, the barrier permeability there. We also talked about net filtration pressure. And in class, we're going to kind of go over some scenarios where we change a few things and see how that affects GFR or net filtration pressure. But I do want to point out that GFR is usually relatively constant. Okay, so what you're looking at here is a graph of GFR on the y-axis versus mean arterial blood pressure on the x-axis. And what you can see is that unless we have a really low blood pressure or a really high blood pressure, in most of these, kind of this middle range of blood pressures, which is a pretty big range right here, we're going from 80 to 180, sorry. If we're in this blood pressure range, our GFR is relatively constant, okay? So our bodies regulate GFR in order to keep it constant. And the reason we want to keep it constant is because we want to protect our filtration barriers from damage, right? So if we blow out those membranes, then we're going to start having leakage of all kinds of materials from the blood into the tubule, which then is going to end up in your urine, okay? And we don't want that. We want to keep those things in our bodies, the proteins, the red blood cells, all of that stuff, right? So we want to protect our filtration barriers. We keep GFR constant through autoregulation of glomerular pressure. Okay, we do that through a variety of mechanisms. We do that by constricting and dilating our afferent and efferent arterioles. We do that by changing our filtration slit size. We do that by changing the state of constriction of our mesangial cells, okay? And this is regulated by hormones and the nervous system, okay? So in class, like I said before, we're going to kind of play around with some scenarios where we change these variables and see what that does to GFR.